In this video, we're going to talk about some introductory statistics where we think about the number of ways of rearranging a set of objects. For example, 3 balls labeled A, B, and C. This is actually going to be very useful for us as we consider physics, where we might want to consider the number of ways of rearranging the air molecules in this room. And it turns out that if you can figure that out, you can figure out a lot about the average properties of the air in this room and what state that air should be in. So we're going to start out with small numbers, and we're going to try to rearrange a small number of objects. And then we will move on to trying to think about how we could rearrange all of the air molecules in this room. It turns out that these statistical models of physics are super useful when you get to a macroscopic number of particles, like say 10 to the 23 particles. That's where things are going to be really useful. We wouldn't necessarily think about doing a statistical analysis on just 3 particles. That wouldn't make too much sense, but we'll start here for simplicity, and then we'll build up to thinking about larger systems. Okay, so step 1, I have just listed all of the ways of rearranging these 3 particles. I can choose A and then B and then C, or A and then C and then B. It turns out there are 6 ways of rearranging these particles. Now, mathematically we can think about this in terms of how many options do we have for each choice of particle. So let me think about just I have 3 spots, and I can put 1 particle in each spot. So for my first option, I have particle A, particle B, or particle C. So I have 3 options for my first particle. Then let's assume I choose A. Then I have B and C left, which means I have 2 options remaining after I've made my first choice. Let's assume I choose B, and then the only option I have left is to choose particle C. So the number of options that I have reduces by 1 every time I make a choice. And the total number of ways of rearranging the system actually just goes like the product of the number of choices that I have at each step. That is 6, which is also equal to 3 factorial. So factorial just means the multiplication of all of the numbers less than that number. So 3 times 2 times 1 is 3 factorial. 4 times 3 times 2 times 1 is 4 factorial. I can do this analysis for any number of objects. So let's say I add in 2 more particles, D and E, and I want to figure out how many ways I can rearrange this. Well, for the first option, I have 5 choices. For the second option, I have 4. So say I choose E for my first choice, then I can choose from A through D for my second, and then 3, and then 2, and then 1, which means that there is 5 factorial ways of doing this. And 5 factorial turns out to be 120. So there are 120 different ways of rearranging 5 particles versus only 6 ways of rearranging 3 particles. So the number of ways of rearranging particles increases very quickly as you add more and more particles. Now let's consider a system where we have indistinguishable particles. So let's say we have 1 particle labeled A, and then we have 3 that are labeled as B, and we can't tell the difference between any of the B particles. And now we want to find the number of ways that we can rearrange these 4 objects that we can actually tell the difference. So for example, if I choose A first, and then I choose this B, and then I choose this B, and then I choose this B, that's a way of rearranging it, but I can't tell the difference whether this B that I chose is any of those values, right? So really, if I choose A first, there's only one state in which I choose A first, because I can't tell the difference between any of the B's. Likewise, I could choose A second, so I could do like BA, BB, or I could choose A third, or I could choose A last. These 4 states I can tell the difference between, but if I am naively thinking that the particles are distinguishable, I would assume that I could get many more states than this, right? So if I considered these four to be distinguishable, then I would say that there are 4 factorial is 24 different ways of rearranging these 4 objects. But that doesn't take into account the fact that this here is only one state, but would really count as I choose A first, right? So my first option is A, and then I have 3 options left. When I do, if I assume they're all distinguishable, then I say, well, I have 3 options here, 2 options here, and 1 option here, right? I can choose from any of the 3 B's, then I pick one, then I can choose from any of the 2 left over, and then I have to choose the final one, right? So after I choose A first, there are 3 factorial, 6 different ways of rearranging the B's, but I can't actually tell the difference between any of those states, right? So in this 4 factorial, I have counted as if I could tell the difference between all of those B's, but I can't. And the way that I fix that is I actually divide my 4 factorial through by the number of, the factorial of the number of objects I can't tell the difference between. That is 4 factorial divided by 3 factorial. And if you're concerned that, well, I only argued it for this one state, it's true for any of these states. If I go to my second state here, if I keep A in the second spot, there are 3 factorial ways of rearranging these B's. And that is true for every single state. So every state, when I did this 24, I have over-calculated the number of unique states by a factor of 3 factorial. So my total number of states is 4 factorial over 3 factorial, which is 24 divided by 3 factorial is 6, is 4 states, just like I said here. We can extend this idea of indistinguishable particles that we can't tell the difference between, to any number of particles, even if we have particles of 3 different types, for example. So there are 6 total particles here. So we would naively think that there should be 6 factorial different ways of rearranging these particles. However, let's just write down an example. So I'll just pick A, C, C, B, 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 right? This is one of the ways that I could reorder it. But within this, I can reverse the 2 C's and I can rearrange those B's as well. How many ways can I rearrange the B's? I can rearrange the B's 3 factorial ways, and I can rearrange the C's 2 factorial ways, which means that my actual system has 6 factorial divided by 2 factorial divided by 3 factorial different ways of actually being rearranged that I can tell the difference between, right? So this state, I can rearrange the C's and the B's. A unique state different from this would be like C, B, C, B, B, right? So this is another unique state. This state, I could flip the order of these C's and I can move the B's around. So it also gets overcounted by the same factor of 2 factorial times 3 factorial. And this is true for every state, right? So because every state gets overcounted by the exact same factor, when we take our 6 factorial, we're able to divide the 6 factorial by this factor.